Okay, the next topic that we want to look at is the concept of a distributed load. That is a force that's distributed over space acting on, some object. And so here is an excellent example of this. We have this beam that is got sandbags piled upon it, but the sandbags are not uniformly piled up. So for example, right here, there's more weight acting on the beam right there because there's more sandbags than there is right there. There's more weight here than there is right there. And so the amount of weight varies with the x position. And in fact, it might be possible, in principle, to come up with a function which we might call some w of x. And so w of x is the weight as a function of position x. Now, this weight is applied along the x-axis. And so we have w of x acting along the x-axis, and we can calculate two things. We can calculate the total weight acting on the beam, and that's simply going to be the integral of that w over x. And so we have this formula F, that's the total force or the total weight acting on the beam. And so it's simply that. So if I know the function w, I can simply plug it into that integral, take the integral over the length of the beam, and that'll give me the total weight of all of those sandbags. Now the next thing that we can consider is what is the moment caused by this distributed load? So for example, let's pick an axis of rotation. Let's say that point right there, that end. And let's pick a particular spot. So let's say I'm going to pick this spot right here. And so there's a certain amount of weight acting right down. And so that would be the w of x at that position x. And it's at some position x there. And so I've got my w of x acting at x. And I could calculate the moment, which would just be the force times the moment arm, which in this case would be x, because w is acting down perpendicularly. So if x times w of x is the moment of that particular weight, the total moment would be simply the integral of x times w over dx. That would be along the entire length of the bar. Now, we can consider that as equivalent to some total moment. So the total force F, so we calculated up here, we calculated the total force acting on the beam from all of those sandbags. If I take that total force and plug it in, there has to be some distance, and we'll call it x bar, and you'll see why we call it x bar in a moment. That distance x bar times F has to give you the same value as the integral that we just calculated for the total moment of all the sandbags. And so we know that this f here is equal to this integral of w dx. So if I plug that in for that f and then solve for x bar, I end up with this expression down below. And that's an expression for x bar. Now what exactly is this x bar? That's the location where you could place the total force F and give the same moment as the moment from all the individual little sandbags. In other words, that x bar is the place where you could put that total force F and get the same moment arm giving you the same total moment as the integral that we did up above. So these are the two relevant quantities. I've got this distributed load here, which I've written as the weight as some function of x. I can calculate the total force or the total weight of all those sandbags, and then I can calculate the moment of all of those sandbags acting at some point, say in this case the leftmost point, and then I can figure out where I could place that single force F and give me the same total moment. So hopefully that's clear, but we're going to apply this to some examples, and that will help us. But before we do the example, there is one thing that is worth noting. Okay, let's look at what we have before. We have some function w, which is the weight as a function of x. So I've got this w here, and it gives me the weight as x. So if I come out to some x and I go up here, that tells me what the weight of those sandbags at that particular spot is. That's what my w of x is. Now, if I'm doing an integral w dx, I can note that the height here is going to be w, and the width is going to be dx. So that w dx is just the area of that little slice, dA. And of course, so if I integrate the entire area dA, that gives me just the area under the curve. And so, if I now calculate the x bar, which we saw in the previous slide is x times w dx divided by w dx, well, that's just going to be x times dA over the integral of dA, and that's the formula for the centroid. In other words, that x bar that we calculated, again, that's the location where we can place the total F of the entire distributed load and get the moment of the entire distributed load. Well, that x, that location, is simply the centroid of the area spanned by the curve w of x. Knowing that can make doing some of these distributed load problems more simple. So let's look at an example. Okay, let's look at this example. A beam is subjected to a triangular distributed load whose value at B is 100 newtons per meter. That means that the distributed load function W, that's the weight as a position X, increases linearly so that there's 0 weight acting at point A and 100 newtons per meter acting at point B. And the amount of increase is linear. So if I go half the distance, I've got half that down. So we want to calculate the reaction force on the beam at point A and the reaction force on the beam at point B. Now there's something in the picture which is not obvious, and this is not really explained in your textbook, and it would be super easy to miss. Notice that position A is fixed, but position B, the beam is basically on little rollers. So that means that the ground is not creating a horizontal reaction force at B. There's only a vertical reaction force at point B, because if there were a force on point B in the horizontal direction, it would just roll a little bit. But at point A, it's completely fixed to the ground, so the ground is going to provide a reaction force both vertically and horizontally. Now, we can use what we saw previously to calculate the total force of this load simply. We know that the total force of the load is going to be the integral of this triangular function times dx, but that's equivalent to the area under this triangle because of our area analogy. So we know that the area of a triangle is simply 1/2 the base times the height, and so in this case the height would be the 100 newtons per meters, the base would be 12 meters, and the area of the triangle would be 1/2 the base times the height, and that gives us 600 newtons. So this entire triangular distributed load, if I had sandbags piled up, so here I've got 1 sandbag, 2 sandbags, 3 sandbags, whatever, such that this weight function is the weight acting on this beam, the total weight would be 600 newtons. Now, to find the moment acting on this point A, we need to find the centroid of this triangular area. And we actually did that in example 1 in your textbook, so you can look back at that, but we found that the centroid for the x position was found at 2/3 the length of the base. And so that would be 2/3 times 12 meters, and that gives us 8 meters for the location where we could put this 600 Newton force and have the same equivalent moment at point A as this entire distributed load. So we can set up what is effectively an equivalent system here of forces. We know that we have the single equivalent force of 600 newtons, which is located at 2/3 12 meters, or at 8 meters, and that force gives the same effect as that entire distributed load. So we have 600 newtons down here at 8 meters, and then we know that we have the reaction forces. There's the horizontal reaction force at A, the vertical reaction force at A, the vertical reaction force at B, and remember there's no horizontal reaction force at B, so we don't have to worry about that one. So if we simply do the sum of the forces in the x direction, we know this is a static situation and the sum of the forces in the x direction has to be 0. The only force acting in the x direction is A sub x, so that tells us that A sub x is going to be 0. Now if we do the sum of the forces in the y direction, we get AY plus B minus 600 newtons is equal to 0. There's the minus 600 newtons because it's pointing down. AY and B are both pointing up, so that would be the sum of the forces in the y direction. And now finally we can do the sum of the moments about point A over here. Now notice the force line of action of AX and the force line of action of AY go right through that point. That means AX and AY contribute 0 moment about that point. But B has a moment arm of 12 meters, and the 600 Newton force has a moment arm of 8 meters. Remember, it's the force line of action, and it's the perpendicular distance from the force line of action to the axis of rotation. So that distance there is the moment arm of that force down. If I've got this force here, the force line of action is like that. The moment arm would be the perpendicular distance from the axis to the force line of action, and so that 12 meters, that would be the moment arm of B. And so if we calculate the moment of all the forces about point A, it gives me 12 meters times B, and that's going to be positive, because if I just have it hinged right here, and I let this force B go, this is going to rotate in the counterclockwise direction. And by default, counterclockwise is considered positive. That's because if I have a normal angle coming from the x-axis, we measure angles theta from the x-axis in the counterclockwise direction, and that's a positive sense. In other words, the idea of increasing angle is to go counterclockwise. So the torque or the moment from that that force B acting at 12 meters, that's going to tend to create a counterclockwise rotation, and so that would be a positive moment. Now, ignoring B and considering just this 600 Newton force acting here, pulling it down, if it were free to move about that hinge, that would create a clockwise rotation. And so that moment, or that torque, is going to be negative. And so I would have this torque of 8 meters times 600 newtons, that's the moment arm times the force, that's creating a negative sense of rotation, or a clockwise sense of rotation, and that's why we have a negative sign right there. And so that gives us all of those moments. And of course, as we mentioned, these two guys over here, they provide no moment about the axis at point A. So I've got this equation and that equation, two equations and two unknowns. I can solve this one for B, plug it into there, and that'll let me solve for AY. Once I have AY, I can plug it into there and solve for B. And what I get when I solve those two equations and two unknowns is 200 newtons and 400 newtons. 200 newtons for the reaction at A and 400 newtons for the reaction at B. And again, all we did here is what we've been doing over and over. The sum of the forces equals to 0. The sum of the moments equals to 0. Plug and chug, solve for the unknown forces that we're looking for. Okay, let's look at another example. This is example 7.7 from your text. And in this example, we have a distributed load acting on a beam, but it only works on half of the beam. So it goes from A to this position at 10 feet, and then there's another 10 feet of beam. And we also have at the far end of the beam a 2,000 pound force in the opposite direction, opposite to the direction of the weight acting on the first half of the beam. And then we have a couple of 10,000 foot-pounds acting at the beam. And so the first thing that we want to do is calculate the effective weight of this distributed load and the effective moment of this distributed load. And so we simply plug them into our formulas, W dx. So this is the weight that's given in the problem. W is 300x minus 50x squared plus 0.3x to the fourth power. And that goes from 0 to 10. That's the length over which that distributed load works. And when you calculate that integral, it should be fairly straightforward how to do that. You get 4,330 pounds. And to get the moment about A, we simply multiply x times the W of x, which is there in parentheses, over the length dx, and we integrate again from 0 to 10. This is, of course, the formula that we have for calculating the moment of the distributed load, and we multiply this x through, do the integral, and we end up with 25,000 foot-pounds. Now, notice that this is positive. Again, positive moments mean that you have a sense of clockwise rotation, and so that tells us that that moment is going to be clockwise about that point A. So let's look at all the pieces we have here. We have the weight of this distributed load. We have the force of the 2,000 pounds at the opposite end. We have the couple of 10,000 foot-pounds. We have the reaction force at A. And we have the moment at A that we are wanting to calculate. So we, again, simply apply the sum of the forces in the x direction, the sum of the forces in the y direction. In the x direction, we have the sum of the force AX is equal to 0. And the sum of the forces in the y direction, we have AY, which is obviously going to be in the positive direction. Again, that's essentially the reaction of the floor pushing up on the beam at point A. And we can say that we have minus 4,330 pounds down. That was the weight of our distributed load. And then we have positive 2,000 pounds upward. And obviously the weight's going to be downward, that's why that's minus. And this is upward, that's why that's going to be positive. The sum of the forces is equal to 0. And actually we can solve that for AY pretty straightforwardly. And then to find the moment of the moment acting at point A, we can say that MA minus 25,000 foot-pounds plus 20 feet times 2,000 pounds plus 10,000 foot-pounds, those are all the moments. So we have this moment at A, and we have this is the moment of the distributed load. And again, it's minus because if this distributed load were the only thing acting on this bar and it were hinged at A, it would move in the it would move in the clockwise direction. It would move downward. And so that would be If it's hinged at A, it would rotate in the clockwise direction, so that's going to make that minus. This 10,000 foot-pound moment here is in the counterclockwise direction. That's the sense of rotation that it's given, and so that makes that positive. And then, of course, we have this 2,000 pound force, and the moment arm of it is going to be 20 feet. So 20 feet times 2,000 pounds is going to be the moment of that force. And it's positive, again, because if that's the only force and it's hinged here, the stick is going to move in the counterclockwise direction, which we, by convention, take to be a positive sense of rotation. So simply writing down the sum of the moments about point A, we can solve for MA, and we get minus 25,000 foot-pounds. And again, what does that minus sign tell me? That tells me that that's going to be in the negative sense of rotation, or a clockwise moment at A. And that's basically it. That's the problem solved. In each of these cases, we used this idea of the distributed weight function, and we applied that to get the moment caused by that distributed weight function. And then we simply applied the sum of the forces equal to 0 in both the x and y directions, and then the sum of the moments equal to 0. Those are our equilibrium conditions that we've seen over and over again. And that's how we deal with distributed loads.